Okay, hello again, guys. I'm Mahmoud. Uh, this lecture is sponsored by Chain of Education. It's about calculus. And in this lecture, we will be talking about sequences. So, sequences is something you covered back in high school, and we'll get back to it. Mainly, we'll talk about the the convergence and divergence of sequences, and how to find the infinite term of a sequence, or how to evaluate the limit of a sequence as n tends to infinity. So a sequence in general is the evolving terms that evolves in a pattern. A pattern, I mean by a pattern that this looks like somehow a function. It can be a function, and it may not be a function. However, we know that it evolves in some kind of a pattern. So sometimes I will have like -1 power n times 2 power n. So for n equal 1, I will have like -2, then I will have +4, then I will have -8, and so on. So this behavior is called a sequence. And every term, so for every n we will have a term. So the term associated with it, we can index it. So I can say that this is A1, this is A2, this is A3, this is A4. And below is a visualization for a sequence. Uh, and you see that the sequence start here, then here, then here, then here. It decreases somehow. Okay, so yes. And what you should always keep in mind that the n that evolves in this sequence is must be a whole number. Okay, so n is equal. Okay, so n is equal to 0, 1, 2, 3, and so on. It's never decimals, it's never integers that are negative, and that's just to be clear. So those sequences could converge, could diverge. You could see the pattern that we are moving through till now. We talked about convergence and divergence back in the improper integrals. So here we come back to the concept of convergence and divergence. So you see, in this case, the sequence terms tends to 0. So in this case, the sequence terms. So if I try to find the I don't know, a very large, the infinite term, this term would be equal to 0. So this sequence is said to be a convergent sequence, and it converges to 0. So the sequence could be like this, and it converges to some number here. Let's say this is C. So it converges to C. In other cases, the values of the sequence grows infinitely. So here I took only a finite number of terms. I guess these are 50 points that I plotted. So you see that in this case, it starts from 0 and it starts growing. And you see that the behavior is that this function will this sequence will keep going, and the terms will keep growing till it reaches infinity. So in this case, we say that the sequence is divergent. The sequence could diverge in another way. So if you see here, like we have this example, the famous example of -1 power n. So we have here the function, the sequence terms evaluates either -1 or +1. So -1 when n is odd, and +1 when n is even. And as you can see here, then here, then here, then here. It keeps propagating, it's keep alternating, we say. And infinity is not even and not odd. So we can't know whether the limit for this sequence is equal to -1 or +1, and hence the limit does not exist. Also, in this case, we say that the limit is the sequence is a divergent sequence. Okay. So in this lecture, we will talk about four main methods to evaluate the limit of a sequence. The first method is the sandwich theorem. The sandwich theorem, it comes from its name. So, like, we have the sandwich that have an upper bread and a lower bread and some content in the middle. Okay. So, it's mainly about is that we have a bounded sequence. So we have a bounded sequence. This x should be n. It doesn't need to be n, but I mean, it's a natural number that I'm dealing with. It's not a continuous domain, okay, for a of x or c of x. However, it could be a domain in general. So if we have a bounded function, b of x, that's bounded between two other functions, a of x and c of x, and all these functions are continuous. However, there are something special about that the limit of a of x is equal to the limit of c of x is equal to L, some L. So like in this case is equal to 0. Here is my a of x, and here is my c of x. So if the limit of a of x as x tends to infinity is equal to the limit of c of x as x tends to infinity is equal to some constant L, in this case 0, then the limit of b of x must be L, okay, by definition. How could this change? It's the b of x is greater than L and less than L, then b of x is equal to L. Okay, less than or equal, less than or equal. So you see in this case, for example, you can try it. I took the function sine of x over x. We know that sine of x over x is bounded between -1 and +1. So the whole fraction is bounded between -1 over x and 1 over x. So I have my a of x is equal to 1 over x. I have my c of x is equal to sine x over x. And I have my, sorry, b, and c of x is equal to 1 over x. See that my a of x tends to 0. Also my b of x tends to 0. So here is plus and here is minus. Tends to 0 as well. Then for sure sine x over x tends to 0 as x tends to infinity. And this is called the sandwich theorem. Another way to evaluate the limit is to approach the composite functions. Sometimes we see functions of len, some functions of exponential, and you remember the substitution method, we have this u of x. So we have the initial function in terms of u of x, and we managed to remove the x and focus on u of x. So this is what we will be doing now. So if I have a composite function, g round h of x, or g of h of x, then it's enough for me to know the limit of h of x, to know the limit of f of x as x tends to infinity. So here, f of x, g of x, all are sequences. So we are talking here about terms. We are not talking about continuous functions. Okay, that is to keep in mind. Because we mainly use x for functions. So yes, for example, if I had len x plus 3 over x minus 2, I know that my main variable is x. However, if I took u of x, okay, and said it's equal to x plus 3 over x minus 2, now I can focus on the limit of u of x as x tends to infinity. And this, in this case, it's equal to 1. Then I can directly say that the limit of len x plus 3 over x minus 2 is equal to len 1 and is equal to 0 in this case. So here is what I mean by manipulating manipulating composite functions. So there are two famous rules, okay? This is rule 1 and this is rule number 2. Okay, it says that if I have f of x and f of x have the powers, okay, you see here n and 1 over n, it's better for me to write it as e ln f of x. Okay, because this way I will get rid of the power and it will be e power something times, okay, power the function that I'm having. Okay, so in the first case, we have 1 plus x over n over n. Okay, so we have 1 plus x over n over n. You should know that this function goes to e power x. And the concept we used solving this function, okay, and here, no matter what n is, it could be k plus 3, it should be alike here and here, the power. Okay, why is that? So I don't want to complicate things for you, okay? So I will solve the easier part, and for you, for some of you who like challenge, you can try to solve in the same pattern. So n power 1 over n. This function goes to 1 as n goes to infinity. Here as n goes to infinity. Okay, why? So if I took this and I tried to find the limit of n power 1 over n, this will simply be the limit of e 1 over n ln n. And this is a composite function of e and u is equal, in this case, 1 over n ln n. And we have that special formula that emerged from Hopital that says that the limit of ln n over n as n tends to infinity is equal to 0, right? Using Hopital, I will have 1 over n in the numerator and I will have 1 in the denominator, so it will be the limit of 1 over n over 1, which will be equal to 0 eventually. So the limit of 1 ln n over, so the limit of ln n over n is equal to 0. This means that the limit of e power n power 1 over n, sorry, the limit of ln n power 1 over n, which is equal to the limit of e power 1 over n ln n is equal to the e limit ln n over n, which is equal e power 0 is equal to 1. So you see, in case of rule number 2, I raised my function, I changed its form from f of x to e ln f of x, and then I used the method of composite functions and find the limit. And it tends to be that whenever I have 1 plus x over n power n, this goes to e power x, and whenever I have n power 1 على n, as n tends to infinity, this tends to 1. So these are two main rules to evaluate a sequence, the limit of a sequence at infinity. So let's get back to the rate of growth of the function and the axis of power. We said slower to faster. We will use this axis in order to evaluate the limits. So you see, we have seen before that evaluating ln and x power x for anything, there would be a very big difference in values between ln x and x power x or x factorial or anything. This means that if I want to evaluate the limit at infinity, we know that the value of lim x is way more smaller than x power x, for example. So in this case, if I was asked to evaluate the limit of as n tends to infinity of x power n over n factorial, so here we have k power x. This is my x power n because my variable is x power is x in this case, and x factorial will be n factorial. So you see, we have this x power n would be greater than n factorial at infinity. This means that I think I made a mistake. Okay, x power n as n tends to infinity, n factorial. So yes, I made a mistake here, and the axis of power, those two should be reversed. Those, okay. So we have x power n is greater than n factorial. Sorry, is less than factorial. X power n is less than n factorial. And this means that the limit of x power n over n factorial goes to 0 as n tends to infinity, as well n factorial over n power n, from the fact that x power x is greater than n power n. Sorry, of أكبر من n factorial. Yes. So those two tends to 0 here for every x in R. Whatever x you want to choose, it's yours. Okay. And finally, we'll be talking about the geometric sequence. So a sequence that is of the form x power n. Geometric, you remember the geometric terms that evolves like 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32. Simply multiplying by a ratio, some constant ratio we chose, in this case 1 over 2, or like 3, 9, 27, 81, and so on. So what's so special about a geometric sequence? What's so special about it that suppose we have here, this is my sequence, an is equal to x power n. So if I know that absolute value of x is less than 1, okay? So I know that the sequence terms are keep getting smaller and smaller and smaller and smaller. How? So like 1 over 2, 1 over 4, 1 over 8, 1 over 30, 16, 1 over 32. You see, at some point, I will have like 1 over 2 power 100, 1 over 2 power 1000. These terms keep getting smaller and smaller and smaller. This means that the sequence will converge. So if I have an is equal to x power n and absolute x is less than 1, then the sequence will converge. What happens if it's greater than 1? Okay, well, in this case, it will grow infinitely. So we have 2, 4, 6, sorry, 6, 2, 4, 8, 16, 32, 64. You see, it keeps growing and growing and growing till it reaches infinity. Whether it's, so it reaches infinity. This means that in this case, the geometric series will diverge. Well, what happens if x equal to +1 or equal to -1? So in case x equal +1, okay, this means that the sequence will be constant. So 1, yes, 1 power 2, 1 power 3, 1 power 100, 1 power 1000. So the sequence will be convergent and its value will remain the same. It will remain 1. And in case it's equal to -1, okay, this means that the limit does not exist. And we've seen that before. We'll keep propagating -1 plus 1 minus 1 minus plus 1 minus 1 plus 1 minus 1. It will never be stable. It will always depend if the chosen n is even or odd, and hence the value of the sequence will be -1 or +1. So if the limit does not exist, this means that the sequence is divergent. Another use of geometric series. So suppose we have a geometric series an, okay, that have shape r power n, ratio times power n. What I know, if that this sequence tends to 0, then if I have another sequence a and bn, and this sequence does not tend to 0, tends to some constant, I can directly say that this goes to 0, right? And this means that the sequence Cn equal an times Bn will be a convergent sequence. However, what is more important is that if I had an alternating term, like -1 power n, in this case, times some sequence an. In this case, if an tends to 0, okay, all right, so Bn will definitely tend to 0. However, in other cases, if an doesn't tend to 0, suppose it tends to plus or minus infinity. So in case of plus infinity, this means that the limit will be minus infinity or plus infinity, will be undetermined. In case it's constant, it will be like plus c or minus c. So in all cases, if the limit is not equal to 0, the limit will still be undetermined, and hence the sequence will be divergent. So if Bn does not tend to 0, or An does not tend to 0, then the sequence will be divergent. Sorry, this lecture was a very long lecture. I hope you enjoyed it. I hope you are benefiting from it. Thank you. Study well.